Okay. Can we start?
Yeah, go for it.
Yes, go ahead.
Okay. Hello. My name is Harvie Zhang. My work is the HyperZ operator connects the slow-fast network for full context interaction. Yeah.
Okay.
Okay. The first question is that why the network needs the radio connection? Yeah, we think it's information loss in the each layer of the network. Then I will give an outline of my presentation. Yeah.
Well, with me,
Then,
it will be probably antiviruses. You know, a lot of antiviruses, just just in case.
because there are so many concepts in the slide. Yeah. Then I will give the definition of the full context interaction. Yeah. To achieve the full context interaction, we need the large convolutional kernels. Yeah. But it has the parameter exploration problem. Then I will review the history of the slow-fast network. In prior works, the slow network is the kernel generator. Yeah, it can be act implemented kernel. Then I will introduce the relationship of the self-attention and the fast weight. In this side, we will conclude that the context-dependent kernel is important. Then I will propose the HyperZ operator. Yeah. Next, I will, based on the HyperZ operator, I will construct a slow-fast neural encoding block. In the SFNE block, I propose so many novel components. Next, I will present the Terminator architecture. Why is it called the Terminator? Because it uses important technologies of the past decades, such as ResNet self-attention as a norm. Then I will introduce the slow neural loss. Finally, is the experiment and the nice property of the Terminator network. So the main conclusion is that in the Terminator network, the radio connection will be discarded. Then I propose the HyperZ operator and the Terminator network. Go back to the first question is that why does the neural network need the radio connection?
All right. So it's based on the kernel, right?
Yeah.
Oh, okay.
In the ResNet paper, it claimed that it mainly focus on elevating the performance degeneration, not the gradient vanishing problem. We can see in the plan network
Okay, so but like, what is the purpose of this neural network you're presenting? Because I'm not, getting it, I think. Your own thing, bro.
Okay. We can see that the deeper model performs worse than the shallow model. Yeah, in the plain network. However, in the ResNet, we can see that when the model dips exceeds the 1000, it also has the performance degeneration problem. So, what is the root cause of the performance degeneration? Then I visualize the feature maps of the planet and the ResNet. We can see that the radio connections can alleviate the information loss because the last feature maps have the many have more object details. Yeah, you can see in the last column of the feature map.
Hi. Sorry, one question here. For these, are these gradient maps?
No, this is the sum of the kernel of the feature maps, not the gradient.
Oh, I see. And then just interpolate. Okay, got it.
Yeah, yeah, yeah.
All right, all right. Is this
Yeah.
is a deer, right? Okay.
Oh, yeah, yeah. Oh, okay. I also present the more results of the ResNet. We can see that in the last two feature maps, it has lost the object shape. Yeah, you can see
Yeah,
that
yeah,
because
yeah,
yeah,
exactly.
because the immediate the polling layer. Yeah. So we think the ResNet features are abstract and a lot of the object details. Yeah, such
Mm-hmm.
as shown in the left feature. So we think the more ideal feature map should be have the should the object shape should be preserved. Yeah, and at the noise in the feature map can be
Yeah,
should
but
be
are those
perfect.
like RGB depth maps, or am I seeing something wrong? Or um, I use depth maps too. It's my usually like first number thing I actually do when I do my to the shit like that. I usually have like models made in grayscale. I mean graphics in grayscale, and I use like my own base of those. But is it like generating depth maps, or how does it work exactly?
The feature map is just the sum of all the channels. Yeah,
Oh, all right.
yeah, yeah. We can get the 2D feature map. Yeah,
All right, all right.
yeah, yeah, yeah. Um, so um, uh, we want the final averaging polling layer to obtain the current object descriptor. Yeah. So we must make the network to have little information loss. Yeah. Then we will analyze the ResNet structure. Yeah. We can see that in the ResNet is always use the small kernel. Yeah. 3 and 7. It's also a single branch network. Yeah. Then they are also reduce the feature extraction capability of the network. It also has the intermediate polling layer. So if we want to reduce the information loss, we need a large kernel, multi-branch network, and no intermediate polling layer. Yeah.
Okay.
Okay. To reduce the information loss, I propose the full context interaction. Yeah. What is the full context interaction? It's mainly focus on enhancing the feature extraction capability of each layer. At each layer, the model needs to extract the global and local features, and it and then combine them to and then combine them. Yeah, but this needs the large kernels. Yeah, which results in the module parameter exploration problem. So the solution is that the implemented convolution kernel. Yeah, I think we can use a small network to generate the kernel. Then
Right. All right. So, like, what should I do then? Like, provide bigger model for a kernel or what?
oh yeah, because the large kernel has the model parameter exploration problem. Yeah.
Okay. Okay.
If, yeah. So we need to use implicit the representation, yeah, implicit network to generate the large kernel. Yeah.
Yeah.
Okay. Um. So how to define the kernel generator or the slow fast network? I will review the history of the slow fast network. In 1911, Geoffrey Hinton proposed the slow width and the fast width in the neural network. Yeah, the slow widths are associated with the long-term memory, and the fast width is the short-term memory. Yeah, he thinks that the effective width is the sum of the slow width and the fast width. Yeah, the the right figure is prediction in 2018. Yeah, he thinks the slow fast width is important for the future neural networks. Yeah. Then
That's really complicated, but I'm trying to, do my best to actually understand.
yeah. Then is the you are going to propose the to use a slow network to generate the weight change of the fast network. You know.
Okay.
The slow network is the feed-forward that is the MLB network. Its input is the XT, its output is the weight change of the fast network. Yeah, the fast network, the input is XT, output is YT. Yeah, he has a
Okay.
similar conclusion with the Hinton is that the fast weight equal is the sum of the fast weight at previous time and the and and the the output of the slow network. So the conclusion is that a feed-forward slow network can generate a context-dependent width for another fast network.
All right. So how about that? Like, I mean, what about when context is like irrelevant? I'm referring to the thing like you're doing the aesthetic work, for instance. How can relate it to such a network? How can we how bigger like model can you know uh, provide you better results for you?
Yeah. We wanted to use his definition is that a slow network can be act as a kernel generator. Yeah,
Okay,
because
I get it.
in our we wanted to use the implemented convolution kernel. Yeah, we need to use a slow network to generate the implemented kernel. Yeah.
I understand. Okay.
I just follow his definition of the slow network.
Yeah, I mean, I'm sorry, I'm just very bad at math. I never really was, like technical mind. Just it might
Yeah,
be it might be confusing for me, but I'm trying, to do my best to
I
actually
know.
understand it.
I know.
Sorry, dumb question, but I have two questions. First of all, why did we remove the residual connections? Sorry,
Which one?
the residual connections. Why did we remove them?
to make like variation of the files, probably like trying to decompose the files, probably.
Uh,
Oh,
And of course compose it on higher level, like higher level of coherence, I guess.
yeah. I just follow his idea. Yeah. Then I will introduce the um, relationship of the self-attention and the fast width. Yeah. Um, the fast width is
Yeah,
same
the
as
graphs
the
graphs
definition
works
of
better.
the
I see the idea, with text,
yeah, the self-attention matrix is the fast width matrix. Yeah. So
yeah, yeah.
they have the connection. Yeah. So you can see that the attention in many works have concluded that the attention matrix is a context dependent width matrix. Yeah, it's also
Yeah.
a fast width because it can change at the test time. Because the attention matrix is calculated from the activation. Yeah.
Mm-hmm. Holy shit! I never knew I'm gonna understand things like that, but okay.
Because the attention matrix
I
is
never was I was not familiar with the topic actually, so it's quite interesting, but I'm trying to like get the whole idea of how I could implicate those bigger models of nets into my work.
okay.
Yeah,
Um,
yeah.
mm, yeah. The attention matrix is also a large implicate kernel. Yeah. And this is the previous conclusion. Uh, uh, as we want the implicit the kernel. Yeah. So they have the connection. They have the connection. Yeah. Large implicit kernel. They also have very few trainable parameters. Yeah. So it can yeah it can solve our the face the problem that a large concurrent kernel has the model parameter exploration problem. Next, I want to compare the convolution and the self-attention. Yeah. In the convolution, it always use the small kernel. Yeah, based on the parameter sharing. But in the self-attention, it use a larger implemented kernel. Due to the large implemented kernel, so the attention matrix can modeling long sequence such as the value. So the conclusion is that in the previous slide we conclude that we need the implicit kernel, yeah, to avoid the parameter exploration problem. Then in the self-attention slide we conclude that the implicit kernel should be context dependent. Yeah.
Yeah. At some point, of course, it should be dependent. I think any like dependency, whether it's on the human level or on the model level, is necessary to actually get any results.
Oh, yeah. Okay. So the conclusion is that we need a context dependent implicit kernel. Yeah. This is the conclusion from the previous slide. As you know, the attention matrix is a context dependent implicit kernel. Yeah, but the self attention has some limitations. Yeah. The first is the
It does, of course. But it's always like you get some sleep and everything is gonna, gonna be fine. I think people should just go to sleep from time to time, and things get you know they're always like, if it comes to decomposing yourself and composing on the higher levels, because this is what I think is like the most factor when it comes to being the Terminator actually. um just sometimes you just have to get yourself a little bit more time to rest, rethink things.
okay, okay, okay. I know.
Yeah, yeah, but just saying.
Uh, I know. I just wanted to, uh, um, from the limitation of the self-attention to propose my HyperZ operator because I think the HyperZ operator is a simple variant of the self-attention. Yeah, they have the
Yeah, yeah, I get the point.
they have the
Actually,
connection. Yeah.
yeah, yeah, yeah. Of course, of course.
Okay, I wanted to the limitation of the self-attention is the quadratic the time and space complexity. Yeah,
Yeah, definitely, definitely, of course, and
yeah.
long-term memory too.
The,
Actually,
yeah, the second limitation is that in the vision transformer, it need to divide the image into patches. Yeah.
Okay.
Um. Uh, i- in the vision transformer, the self-attention only obtain the patch level score, not the pixel level score. Yeah.
Yeah, but all things considered, you have to consider the depth of the image. Actually, when the depth is higher, like 24 bits, for instance, when on just bigger models. I mean, not models, but images, in general. When it comes to JPEGs, there is always compression, and that just makes image. You know, you cannot receive so much information out of image like that.
Yeah. Yeah. Because in the previous conclusion is that uh, if the patch is smaller, the model performs better. Yeah.
Well,
The
yes, yes,
patch size is smaller. The patch size
definitely,
is smaller, means
yes, yes,
the
yes.
performance is better. But the self-attention can't obtain the pixel level score because it need to divide the image into the patches. So we want to use a simple element-wise manipulation to get the pixel level score. Yeah.
Okay.
Also,
I mean,
we
holy moly, guacamole! This is so complicated. I'm reading the I'm reading the paper. It's like, whoa, whoa, holy! This is like lambdas and S4s. The last time I actually heard about S4 was back in Area 51. But okay.
okay. Uh, we want we hope in the new network should have context-dependent large implemented kernel. Yeah.
All right.
We also want a new variant of the self-attention. It has a linear complexity and it can also obtain the pixel level score. Yeah.
Oh, all right, all right. So, yeah, like, why do you, for instance, need me to? I mean, should I install something, on my PC, or just, to grab you to give you data or something like that, Because if so, I can do this, so no problem.
Oh, okay. Then I will introduce the HyperZ
You
operator.
can even like install keyloggers if you want. There's like nothing to actually hide in my computer right now. I'm not making news because I haven't done time to do so. So I'm only doing pretty work. If you like need any data, for instance, like any data, like because I'm doing some crazy space stuff, just feel free.
Okay.
because because the paper is actually really complicated. I mean, like, what the fuck am I reading? My mind is just not technical. I'm more like into the values of aesthetics and artistry. I values those things. Other than the text itself, like H plus H, means cycler or whatever.
Sorry, Stick. Maybe
Yeah, I
maybe
know,
let's
but
leave.
but that happens to be the truth. I just saying. Um.
Maybe let's leave the questions till the end for like a
All right, all
Q&A
right, all
session.
right. Yeah. I'm just I'm sorry. I'm just maybe I'm like a little confused. That's it. So I'm
Yeah.
sorry.
I know, I know.
But yeah, let's leave questions till the end, and I think then we can do like a Q&A session. Yeah.
Yeah. Yeah. I introduced so many history and previous
Yeah,
works. Yeah.
that's fair
Yeah.
enough. I mean,
Yeah. I began to introduce the important part. Yeah. Okay.
okay, sure.
Okay.
I'm sorry. Just I'm like I
Okay.
the last time I was a student was like 6, 7 years ago.
Okay. Then is the HyperZ W operator. Yeah. We
Well,
we first.
it's her that is tablet operator. I'm not touching her tablets.
Okay. Yeah. We use a small implicit MLP network. Yeah. It's also called the multi-clitive filter network. Yeah. To
Yeah.
generate the large implicit convolutional kernel. Yeah. It can avoid the parameter exploration problem. Yeah.
Yeah. It's of course.
Yeah. The feature is the equation is the um, how to use the implicit MLP to generate the kg. Yeah, kg equals to HO. Yeah.
So you're like trying to get data just to create like AGI. I assume.
Yeah. The input to the MLP is the coordinates. Yeah.
I feel so relevant right now. I feel I have a role. Yeah. Sorry. Continue.
Yeah. It's the slow network or the implicit MLP network is the input is the coordinates. Yeah, its shape is 1, 2, HW. Yeah.
Yeah.
You just want to use this network to generate the convolutional kernel. Its input is the coordinates. Its output is the kernel. Yeah. The kernel size is 1C HW. You just notice. Then the HyperTW has two different.
HyperZ.
Yeah, HyperTW
Oh
has two
shit! Why
different.
is this so complicated? I mean, honestly, guys, why? I mean, I'm really like I want to. Oh,
Stick.
yeah.
So
Yes,
maybe
you
let's
can
let
call me
him
Michael.
finish the
I think
presentation first.
let's first let him finish and let's keep the questions for the end.
All right. Sorry.
Yeah, sorry.
Yeah. Because we need the multi-branch network. Yeah. So we use the two different HyperTW. The first is the global one. The second is the local one.
Okay, I see.
Yeah. In the global branch, we can see that the hyperkernel is generated by the implemented MLB network. Yeah. First, we can use the element-wise multiplication to get the context-dependent kernel. Yeah. This context-dependent kernel similar to the attention matrix, because they are all context-dependent, and it's also a fast way because it's dependent on the hidden feature or the input Z. Yeah.
Mm-hmm.
Okay, then we use the context-dependent kernel to perform the dot product on the Z again to get the output. This is the HyperZ W operator. There are two Z and one W. W is the hyperkernel generated by the slow network. Z is the hidden feature.
I see.
Yeah. So the context-dependent kernel is a simple variant of the self-attention matrix because we use the element-wise multiplication, not
So
the.
when you say like matrix, you are referring to the matter, right? I mean, like the feminine aspect of technological, I mean, technological aspect, like feminine one. All right, I'm trying to figure out, like hyperkernel. This is so complicated, like
Okay, okay. The context-dependent kernel is a simple variant of self-attention. Can you understand this?
Just continue. I don't want like interrupt.
Okay. The second point is that the context-dependent kernel representation can be regarded as a pixel level score. What is the pixel level score? As the future shown that the hyperkernel is generated by the slow network. The second
I'm
rule.
gonna have to do like proper
The
homework.
second rule is the context-dependent kernel, because we use the element multiplication between the Z and the W to get the pixel level score. Yeah. Context-dependent kernel is the KG hat in the equation 5. KG is the hyperkernel. Z is the input or the hidden feature. Yeah. Because the broadcasting the KG along the batch dimension, so we can obtain the pixel level score of each sample. Okay. We have introduced the global HyperZ W, then we introduce the local HyperZ W. The kernel size is 5, 11, and 9. In the global HyperZ W, the contents-dependent kernel can be obtained through a simple element-wise multiplication of the Z and W. But in the local branch, we need to transform the Z to have the same size of the hidden output of the slow network HI. Yeah, the C is the coordinate, and the output of the slow network is ECKK, is the channel-wise convolution operation. Yeah. On the right feature is a detailed step of how to get the local context dependent local kernel. Yeah, because we need to expand the Z input Z into the generation process of the evolution kernel. Yeah. Can you get it? Then I introduced the slow fast neural encoding block. Yeah. This block have 1, 2, 3, 4 have 4 levels. Yeah, the first is input. We first go through a channel mixer. Then we use global and local HyperZ Ws to extract the features. There are 3 global branch and 3 local branch. Then we concat their channels. Then then the features go through a channel bottleneck layer. Yeah, this is the overall structure of the block. Based on we then introduce the what is the slow net and what is the fast net. Slow net is the kernel generator. Yeah, it's the small MLP model. Yeah, the fast net in our definition is the channel mixers and the bottleneck layer. Then we introduced why the channel mixers. Yeah, because the dot product convolution as the dot product operation and the convolution operations are kernel-wise, so we need the channel mixer. As in the self-attention, it also has the first level is the dot product based multi-head attention, then is a MLP based channel mixer. Yeah, in our block, we first use 3 channel mixer go to a norm and HyperZ and then norm. Yeah. So the structure of the transformer and the SFNE block is similar. This is we have three channel mixer, RGU, hyperchannel, and MLP based channel mixer. This is the RGU. Is the extension of the JLU gated linear unit. Yeah, it have doubling the parameter and the calculation, but it makes the model perform better. Then it's another channel mixer, hyperchannel interaction. The left picture is the ECA net. Yeah, it is known as the channel channel attention. Yeah, channel attention. It first use average pooling layer to get the 1 times 1 times C channel features. Then use a small convolution kernel to extract the kernel features. Then go through a sigmoid function to get the gating score. Then use element-wise manipulation between the gating score and the input X to get the kernel enhanced the output. Yeah. The difference between the ECA net and the HCI is we use the HyperZW to replace the small convolution kernel. Yeah. You know, the HyperZW already have the dramatic width. It also can achieve the full interaction in the channel dimension. Yeah. Because in the small kernel can't only achieve the local interaction in the channel. Yeah. Then is the hyper interaction branch. CBAM is the previous work. It had two sequential submodules. First is channel attention, then is the spatial attention. Yeah, in our hyper interaction modules, they are parallels. Yeah. We also use the high-level output, the gating score, to extract the features from the low-level input X. And you see that high-level output from the global HyperZW. Yeah. We can see that the gating score of the high-level output achieve the pixel-level filtering on the input X. There are also two branches to achieve the full content interaction. They mainly use to reduce the information loss. The SIJLU and the media is the output. Then is the kernel bottleneck layer. And you know, if the input is CHW, we can cut all the features from the global and local branch. We can get non-CHW. This is unsetable because the channel will be also explored. So we define a lambda to compress the channel.
Okay, I see. So it's about fairness.
You can follow me?
I mean, it's about fairness then. I mean, being fair, you know, because you said you.
Oh, okay. What?
Sisler, I don't think what you're trying to say right now, I don't see how it's relevant. So please ask relevant questions. Yeah, thank you.
Yep.
Yeah, the bottleneck layer mainly focus to compress the channels. Yeah, the other the other is that it can remove the noise. You can see that before the channel bottleneck layer, there are also we can get the more retain more details of the object, but there are also contain the noise. Yeah, so after the from the bottleneck layer, the noise are removed. Then I introduced the mixer IS is the information standardization. After each channel mixer I and IS. IS is a variant of instance norm. Yeah. They are mainly focused to ensure the independence of the channel dimension and the sample dimension. Yeah, you know. Yeah. Next, I want to introduce the standardization. Is a new variant of norm. First, before the line is the this car standardization. Yeah, but in the better norm paper, they also add a fan parameters. It include the scale and the shift, gamma and beta. Yeah. In the PyTorch implement, it also have a momentum argument. Yeah. While M is the moving average version, M always equals to 0.9. Okay, if we remove the parameter after below the line, the norm will become a this standardization. Okay. So in our discourse standardization, it will there is no trainable parameter. We can see the results that in the ResNet, if it trained with the BS is the batch standardization, BN is the batch norm, original batch norm. If ResNet use the BS, is performance worse. Yeah, but our Terminator performed better after remove the fan at the moment. Yeah. The other visualization is channel channel mean and channel variance. Yeah, we can see that the ResNet with the BS is the channel mean is about the 0.5, and it trained with the BN is the channel mean is the 0.1. But in contrast, our Terminator can obtain the 0 valued mean. Can see that? Yeah, because the ideal channel feature have the 0 mean and 1 variance. This is the ideal feature. Our network can obtain the more ideal feature. This is the conclusion. Next, I show the Terminator network. Compared with the ResNet, our network is just simply by stacking the SFNE block. Yeah, we use the large implicit kernel multi-branch and no intermediate polling layer. And we also propose a slow neural loss with a local feedback loss to update the slow network. Yeah. Then is the slow neural loss. Slow neural loss mainly to update the global hyperkernel KGG. KGG the size is 1 CGHW. CG is the number of the channel in the G block. How to calculate the slow neural loss? First, KGG is 1 CGHWG. That big G is the number of blocks. E is a channel expansion operation achieved through the repeat continuations. Yeah. After the continuation, the KGT have the same size with the KGG. Yeah. So they can we can calculate their MSE loss. Yeah. Then the slow neural loss will be combined with the cross entropy loss to train the model end to end through the backpropagation. Then I introduced the slow neural loss to verify its performance. In the left subfeature, we can see that when the model trained with the slow neural loss, it can obtain the more accurate pixel level scores. The right table shows that it can improve the model performance. Yeah, about 4 points. Yeah, 4 points. Next is the experiment. First is the results on the 1D image. Yeah, such as the pixel level, minist, p-minist, and S-10. You can see that our Terminator have fewer model parameters and achieve the state-of-art performance, even though the Terminator discards the radio connection. Yeah. There is a result on the 2D image, C10 and C100. Yeah. It performs better than the Inception model, VGG, VIT, ResNet, and the recent state space model. Yeah, Hyena. Yeah. The right table is the result on the STL10 data size. We can see that our Terminator have very few model parameters, but its flops is about twice the ResNet. Next is the model parameters. We can see that the slow network only has 8% of the model parameter. Yeah, but it can generate large convolution kernels. So avoid the parameter exploration problem. Yeah. The other property is training convergence. Yeah, our Terminator converge fast. Yeah. In all the data set, our Terminator only needs one quarter to one half of the training epochs. There is the evidence studies. Yeah. You can see if the Terminator only has the global dot product, yeah, the global HyperZ Ws, the performance very poor. In the third row, we can see most comments and very few flops, but it can significantly improve the model performance.
And it
Then
really
it's
seems like we're hit with news about how
then is the visualization. Yeah, we can see this is the comparison of the ResNet and Terminator. Then is the global and local features. We can see that the global branch mainly extracts the details of the objects, and the global branch only extracts the rough representation. Then they concat then the concatenated the feature retain the more details. Yeah, it's over. Thanks.
Yeah, a question. Just joking. Just joking. I mean, thank you so much. I'm trying to understand this. I'm sorry if I was a pain in the ass, but it's really like complicated for me.
Oh, okay.
Thanks
I
for all
know
the questions. Thanks for the presentation, man.
Yeah, exactly. Thanks for the presentation. It was extremely like whoa.
Great presentation. Thank you.
I know. I know because the people have so many definitions. Yeah.
Yeah, I mean, I mean,
Oh, but I want to highlight the important contributions. Yeah, that we discuss the radio connection. Yeah, we propose the new variant of the self-attention. It can obtain the pixel level score. Yeah.
Do you have like any future plans? Like, oh, now you want to explore something else as a result of this research?
Yeah. And you see, I only have the experiment on the small data set, so I wanted to verify the performance on the larger scale data set, such as the ImageNet. Yeah, but I'm looking for computer resource. Yeah, GPU. It needs A100 GPU. Yeah, but
all right. I have a question for you. I'm sorry. Do you do like graphics works, for instance? Do you use models for generating graphics or images in general? Or you just do it like those kernel things?
You mean?
Yeah, I mean,
use the on the image generation task.
Yeah, for instance, like do you use like stable diffusions or
Yeah, I think it can applied to the image generation task because the main contribution is the large kernel.
Oh, okay. Right.
Yeah,
Yes,
it's a
yes,
large
of course.
kernel. I wanted to highlight the second point is the in our network we discussed the immediate polling layer.
Oh, all right,
So
all right, yes.
so in the generative model, we can don't use the latent space, you know.
Sorry, so can I be used like to? You can create like models out of me, you know, like of my specific, internet, movements, for instance.
Hi, thanks for the presentation. I have one question. Kind of like
Yeah.
for this operator, it's mainly used as like a replacement for transformers, right? So
Mm.
are you interested in doing like next token prediction tasks? Like not just images, but like on like text?
Oh, you mean the use the large kernel into the large language model?
Yeah.
Okay. Actually, previous work has applied the convolution into the language model, such as the you know the hyena. Yeah, it was proposed by the bingo.
Oh yeah, yeah, yeah.
It, yeah, it's a gated convolution model. Yeah, but it performs um, but it performs not well, not good.
Oh,
So
okay.
I think is is the implication have problem. I will try to use my network to the large language model. I think the uh, large large implicate convolution kernel will be important. Will be also important in the large language model. Yeah, I think.
Interesting. Thank you. Actually, one more question. For the dynamic convolution part, basically the idea is you use the global Z and W to like dynamically generate like using something like a RNN for the local weights, right? Or yeah.
I can't understand your point.
Sorry. How do you dynamically generate the convolution kernels?
You mean how to obtain the convolution kernel?
Oh yeah, yeah. Sorry.
Yeah, my large implicate convolution kernel uh, uh, is generated through the slow network. Is also a small implicate MLP. Yeah, you can refer to the paper CCN. Yeah, I follow the um implication of the slow network. Yeah,
Okay, got it. Thank you.
CCN and the FlexNet. They call they call their model as the continuous neural network. Yeah, but in their model they don't use the large implicit kernel to discuss the radio connection.
I see. Oh, interesting. So they also do something a bit like this paper, except for the residual connection part. But
you know,
yeah, fix. But thanks for the reference. Fix. Uh, Actually, one final question. Uh,
okay, okay.
for the normalization, you explained that removing those parameters were helpful, but why were they helpful again? Sorry.
You know the pattern.
Yes.
Yeah. In the pattern paper, they think that the FM parameters, yeah, the gamma and the beta, mainly focus to I mean to recover the model. I forgot model representation learning. Yeah, but I find that the FM parameter mainly used to get the smaller channel mean and smaller channel variance. Yeah, my 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 visualization is different from from their claims in the Bing paper.
Oh, maybe I got it. Thanks. Okay. So interesting. Does anyone have any other questions?
When we go to the war. No, I mean, I'm trying to, get myself into, more technical type of, thinking right now because, like I said, going straight from aesthetics into the technical stuff might be sometimes, pretty hard.
I know.
It's just, it's just so, it's like huge shock, it's like, unlike anything I have seen before, which is a good thing, because it forces you to actually, think like different, people, and that's good,
Okay, I know.
I don't understand.
So no other questions?
Now we can
So,
go all play games,
okay,
I would consider, Counter-Strike, for instance.
Yeah, for sure.
Yeah, I'm sorry.
Okay, then I thank you, Javi, a lot for the presentation. Yeah,
Oh, for sure,
yeah, like honestly, it was
it
very
works. It works like that, For artists, I think it works like that, It just this small part of of being yourself confident, and try to actually force maybe your ideas too. Actually, that not really dependent on such a highly technical jargon. If you know what I mean, of course. I thought not.
Well, anyway, then I think that's it for the presentation and questions, right? Oh, Adam, do you want to do the? Is Adam here?
I don't think he's here right now.
Oh, okay,
So
okay. Then thank you all for coming, and I don't think we have a next presentation scheduled yet, but
Well,
yeah,
I can always talk, I'm just a good talker, in general. So,
yeah,
present could be, with my like the voice.
yeah, for sure. But yeah, thanks for the presentation. I think that's it. So hopefully see you guys next week then. See ya.
thank you,
Thanks.
everyone.
Okay,
Thank you,
okay.
Harvey, for the presentation. It was really great. I'll certainly look into it. Thank you. Take care, everyone. Bye bye.
Bye bye.